Okay, we're going to work on chapter 4 now. We're going to talk about writing equations to describe patterns. Now, writing equations is a really important part of math because it leads into solving with algebra later on. But let's look at this first one here. So what we have is we have a table, a nice square table here, and we want to know how many people can we fit around the table. So on table number 1, we can put 4 people around it. Well, then we put 2 tables together. Well, obviously, we can't stick anybody in the middle, but then how many people can we fit around it? Well, now we can fit 6 around it. And in this one, we have 3 tables together, and we can fit 8 around it. So there's a pattern there, right? So as you increase the number of tables by 1, the number of people increases by 2, right? So we went from table 1 to table 2, it increased by 2. We went from table 2 to table 3, it increased by 2. Another way to do it is we can create what's called a table of values, or TOV when we shorten it up. So tables, people. So table 1, 4, table 2, 6, 3, 8. And you see here, we've added 2 more. Where did those come from? We didn't have any pictures. Well, we can see the pattern is going up by 2. Then we can create what's called an expression. Now, the big difference between an expression and an equation is that equal sign. The expression is just the variables and the numbers. So we define our variable t equals tables, and then to create this, we create basically an expression 2t plus 2. And what this does is it allows us to figure out for any number we want of people. Equation, p equals people, so the number of people equal 2 times the table plus 2. So if we had 13 tables, we could figure this out, right? So there's the equation. We replace the t with 13, right? We substitute it in. 2 times 13 is 26, and then plus 2 is 28. So we could figure that out. So if you're working for a restaurant, you wanted a big party coming in, you can figure out exactly how many tables you had to put together to put the party in there. Okay, flip the page. We'll do another example here. This is a little different one here. We're talking about gardens. So what we have here is we have 4 boards, right? The boards are on the outside here, and that can create 1 garden. Now, if we have 7 boards, right, and we stick them together, we can actually make 2 gardens because this center one shares both gardens here. If we have 10 boards, we can make 3. So as the garden increases by 1, the boards increase by 3. That's our word pattern. Table of values, gardens 1, boards 4, gardens 2, boards 7. So you can see this is going up by 3. And again, we can do these extra pieces of information down here at the end, even though they weren't on there. Expression, G equals gardens. So 3 times G, 3 times the garden plus 1. Okay, the equation, we add the equal sign and another variable, b equals boards. So the number of boards equals the 3 times the number of gardens plus 1. So how many boards are in 12 gardens? So we substitute in for the g there, we substitute in 12. And we go 3 times 12 is 36, then we add 1 to it. So we need 37 boards to make 12 gardens. Well, the interesting thing about this is you can also work backwards then. If I used 28 boards, how many gardens did I get? Oh, well, this is backwards. So the difference is instead of replacing G, we're replacing B and replace it with 28. Well, algebra, I mean, you have a basic understanding of algebra. We're going to look at it further in the next chapter. Here, what you do is you got to get the 1 by itself. So we subtract 1 from both sides. So then we end up with 27 equals 3G. And then how do we get G by itself? Well, we got to divide both sides by 3. And we end up with 27 divided by 3 is 9 gardens. So if we had 28 boards, we could make 9 gardens. So once you get the equation figured out, you can work forwards and backwards to figure out any number of problems. Okay, last page. Kelly's cab. So I don't know if you've ever taken a cab, but when you get in a cab, there is a set price automatically on the meter. And in this case, it's called a fixed cost. And it's right here, $3.60. So if you go 1 kilometer or you go 100 kilometers, right, you still have to pay that $3.60. And then there's so much per kilometer. So we can define our variables. D is distance, C is cost. Like when you pick variables, pick ones that make sense. Don't pick weird letters for other ones. D, distance, C, cost. Okay, so distance. If we go 0, we still have to pay the $3.60. I know that's not really going to happen. You're not going to get in a cab and then decide, no, I'm going to get out of the cab and pay the $3.60. That's a waste of money. If you go 1 kilometer, it's the $3.60, right, plus $1.50, which is $5.10. If you go 2 kilometers, it's $1.50 times 2, which is $3 plus $3.60, $6.60. And you can see the pattern goes up here. So the expression here is $1.50 times the distance, right? That is your variable cost, plus your $3.60. That's your fixed cost. That's why there's no variables with this, right? This one has a variable or a letter, and it changes. Here's our equation. The cost equals $1.50 times the distance plus $3.60. So if we knew we were going out for the evening and we needed to have some money so we could get home, what's the cost of an 11 kilometer taxi ride? Well, there's our equation there. We're going to replace D with 11. So we plug in 11. So $1.50 times 11 is $16.50 plus $3.60. So we need to have $20.10. So if you only had a $20 bill, you couldn't take an 11 kilometer taxi ride. You don't have enough money. Okay. So what you're going to do in this one is you're going to create equations and then figure out answers based on those expressions and those equations. And we can do this a number of ways, like we said, with words, with tables of values, right? You can even do it with a picture. Okay.